Here we are back in northern Utah. What are the odds of it raining? We're in an LT1 10-speed in a relatively heavy JK. Got some 40-inch tires. This one's got 22-inch rims, so we don't have a whole lot of sidewall on it. It got pretty decent economy on the way up, and I think a lot of it has to do with the economies that the LTs offers, as we discussed in the last video. So we're going to be taking this one down to Vegas, doing some trail running with it. For those of you wondering, this is the Provo Pass. I wanted to mention this ABS light on the dash. We scanned it, and it has a lost communication with dynamic sensor code. Now, the dynamic sensor, as most of you know, controls a lot of the ESP. It has yaw sensors and other signals that it sends to the ABS module or to the network. And in the old days, and I guess still today, if you cut the wire going to the dynamic sensor and shut it down, essentially, that disables ESP. Some guys will hook it up to a switch. It's called the ESP bypass. And that way, when you want to completely disable your ESP, you can. Sometimes ESP can get in the way, like if you're on an icy road. Yeah, you want ESP and traction control, but sometimes traction control can kick in at the worst time. You could be in the middle of an intersection, lose engine power, and have no way of getting out of there. I grew up in a time where we didn't have ESP, or at least most vehicles didn't. There were some vehicles that experimented with ESP all the way back to the 1960s. I think the origins of ABS braking was aircraft, so that pilots didn't burn the tires up on the runway. In any event, you just had to know how to drive. Now, are there situations where ESP is beneficial? Well, yes. But I have found myself in situations where I'd prefer not to have had ESP. In the real early days of the JK, 2007, 2008, Chrysler realized that modded vehicles, guys would put 40s on, they would not recalibrate their speedometer, and ESP would misinterpret what was going on with the vehicle. So it could prematurely engage your brakes or cut power. And if you're coming off a freeway on-ramp, the last thing you want to do is brake into the oncoming traffic. So Jeep quickly came up with the ESP bypass of their own. A lot of guys call it the steering wheel dance, because you have to push the ABS button and turn the steering wheel this way and that way, and it's really a pain to get it to work. And when it does work, the lights on the dash, every time you key up, say ESP off and ding, and they are a nuisance. But that's what Jeep's solution was for modded vehicles, where ESP could become a liability. Now, cutting the wire to the dynamic sensor essentially gives you the same benefit. However, if you flip the switch and re-engage the dynamic sensor, then key the vehicle down and back up, you now have ESP again. So it's kind of the best of both worlds. Some guys completely disable their ESP. I have a few customers doing bills where they're running aftermarket axles and they don't even have tone rings. The vehicle speed is sensed in the JK through the ABS module. It has 4-wheel speed sensors. Each corner or each wheel has a wheel speed sensor that feeds back to the ABS module, and that tells it how fast you're going or how fast each individual tire is going. So it can interpret when you go around a turn, and it can then synchronize that with the steering angle sensor, or the SAS. The wheel speed sensors and the steering angle sensor work together so the ABS module can interpret vehicle dynamics. It can tell if the vehicle is skidding. It can tell if you want to go one way and you're going another way. There's something called BAS, or brake assisted steering. A lot of you guys don't know, but the vehicle will try to brake and keep you going in the direction that the steering wheel is pointed at. There's other things like trailer sway control. There's brake locking differentials, BLD, and I've talked about this in my videos, and that's probably a whole nother video, but it's something that Land Rover's been doing for a long time, and that is, without having mechanical lockers, the BLD can apply brakes to transfer power around the vehicle and get you the maximum amount of traction, and it works. Does it work as good as a selectable or an automatic locker? No. But does it work? Yes, I've actually tested it. Also, I think anti-lock brakes are almost a necessity. There's been many times that I've had to 2-foot the brake pedal. In fact, just the other day on the freeway, a car pulled from the right lane all the way to the left lane to get in an off-ramp, a left side off-ramp, pulled right in front of me, and I got on the brakes hard and I heard that ABS engage. And especially with the larger tires, it helps you maintain control. Now, I think off-road is a different situation. Off-road, you want as much traction as you can get. And in a lot of situations off-road, spinning the wheels can help. If you're in mud or snow and you need those wheels to spin, ESP can be a definite downside or a negative. That's why when you put the vehicle into four-wheel drive low, it essentially disables all the anti-lock. Well, basically it disables ESP altogether. I do believe the BLD continues to operate, but that's kind of fuzzy because Chrysler's constantly changing their programming. However, when you're off-road, you want as much traction as possible. You want full control of the throttle without the computers getting involved. Now, I will say the Land Rover has been doing this for a long time, and they got a lot of experience with it. And Land Rover has luxury vehicles that can go off-road. Now, a lot of guys don't want to do what they do in their Land Rover that they do with their Jeep, because a Jeep is a $30,000, $40,000, or at least it used to be, dollar vehicle. Live axles, tough. It's not nearly as sophisticated as a Land Rover. Some of these Land Rovers have 20, 30, 40, 50 modules plus air ride suspension systems. And they're just too high-end really to go out and beat up on rocks at Moab or Rubicon. But what Land Rover has done is they've essentially allowed their vehicles to perform adequately off-road by using the braking system. By braking one side that's spinning, you can transfer the power to the other side. Many of you know with an open differential, essentially the power goes to the side that has the least amount of traction. Positractions or True Tracks or whatever you want to call them, Detroit's, they will try to apply the power more evenly or more towards the tire that has more traction. Obviously, a selectable locker is the best, like an ARB or an E-locker, where you can flip a switch and that axle is locked. By locking the front axle, rear axle, and transfer case, that's as much traction as you're ever going to get. And if you're ever in a situation where it's really slippery terrain, whether it's a rock or snow or mud, you want as much traction as you can get, and you want full control of the pedal. You don't want the computer to get involved and start pulling the power back. I remember I was up in Sandy Valley once with a JK and a TJ. No, it was a YJ. We did a YJ and a JK. And that little YJ was so light with the big tires, it just floated over the sand. But the JK, in order to get over some of these berms, you had to basically floor it. And with the V6, when it shifted, it would lose so much power that it would kind of bog the engine down. Then the ESP would kick in, sensing that the tires were spinning. So you had to have it in 4 low, but you didn't want it in 4 low. You wanted it in a 4 high so you can get wheel speed up. So it's just not an ideal situation. With the V8, when you turn traction control off, it's a whole different animal. You can go out there and throw a rooster tail and go up and down these sand mountains without having to bog the engine down. Especially with tap shift. If you are going to, and I'll demonstrate this, and if you look at some of my old videos, I already did, some of the operating systems allow you to do a second gear launch or select maximum gear. Second gear launch is exactly that. It allows you to take off in second gear. Some of the operating systems, like the Corvettes, will let you take off in second, third, fourth, but that's really going to start bogging. The whole object is to not have that shift. And by not having those shifts are where you change wheel speed. When you change wheel speeds, you have the chance of bogging the engine down, maybe breaking the tire loose. You want consistent wheel speed to the ground and proper control. So by launching in second, that'll give it to you. Most of the operating systems we provide will allow you to select maximum gear. So you go into the tap shift menu, you look at your dash, and let's just say you're going to be going up a sandbar or you're going to be climbing a rock, and you know you're not going to want to get out of second gear, but you want the operating system to shift the transmission for you. So you just simply tap up to second gear while you're at a stop. Then when you take off, it'll do the 1-2 shift, and it will not shift from second to third, at least until you override it with a tap shift switch. And I find that very useful on some trails. Some of the trails that I run out in Vegas, I'll probably max out in third or fourth gear, and if it goes above that, especially if I'm going down a trail, I'll overspeed, and then I got to hit the brakes. So what I'll do is I'll just set tap shift to third or fourth, and then that it does it for me. Another huge benefit of tap shift is compression braking, and I just talked to a customer who put some massive brakes on his Jeep. They were Bears, and I really haven't seen that many Bears out there, but I have seen a couple. In any event, He doesn't want cruise control. He didn't want tap shift. He wants as simple of operation as possible. So he put larger brakes on the vehicle so he can go down hills and use his brakes more. Having tap shift means you can go down that hill and use the engine to compression brake it. Some guys think it wears the engine out. Well, whether it does or not, these engines go for hundreds of thousands of miles, so I don't think that's really that big of a deal. One of the things that you'll find with our operating systems that we really haven't advertised too much is that you can use your cruise control switch, whether you have the steering wheel mounted cruise control switch or the stock mounted on the earlier JKs. You can use that for tap shift, and you don't lose your cruise control. You essentially just set your cruise control whatever you want it to be and drive, pull the lever back into the manual gate, and cruise control will remain active. Of course, you can turn it off with the brake pedal, but it'll remain active. And if you switch into the tap shift mode, you can then go down a hill, downshift, and hold your speed back. The computer will hold your cruise control selected speed, but by not being in, for example, in this vehicle in 10th gear, we're not going to be over speeding going down those hills. So there's a lot of versatility in these modern transmissions that guys don't know about. It's one of the beautiful things about the GM operating system is you can pretty much get yourself a tune tool like HP Tuners, EFI Live, tune it however you want. I remember back in the early days of the Gen 4s, I wanted to experiment with lean cruise, and of course GM pulled lean cruise out of the North American vehicles pretty early on, but it stayed in some of the platforms on the Gen 4s, and I was able to fool the system with the alcohol content, have a switch on that, and basically get lean cruise where I can cruise at 18 to 1. And what I determined was it just wasn't that much of a benefit, because with all the monitoring that had to be done so you didn't overheat the catalytic converters and burn out the oxygen sensors, and the fact that you had to switch out of lean cruise into normal mode, closed loop mode, so that the computer could reset, it was just too much effort to try to get it to work properly. And I think that's why the manufacturers decided, well, I don't think the manufacturers decided, I think the federal government decided that lean cruise, and you guys probably remember the old Honda lean burn engines and the Chrysler lean burns and the stratified combustion chambers. They were all trying to take advantage of the lean air-fuel ratios, and they did, and it's incredible what some of the 80s and 90s vehicles did. They were getting 30, 40, 50 miles to the gallon before the hybrids, but the problem was we were building up really high combustion chamber temperature, running so lean, and that was building up NOx, and we all know that NOx is a bad gas, so basically it was phased out. Now, your operating system does have certain open loop modes where the engine is not stoichiometric. Remember, with a narrowband oxygen sensor, you are trying to target one air-fuel ratio, and that is 14 point, well, it depends on the fuel you're running, 14.7 approximately with pure gasoline. You get a little alcohol in there, ethanol, you're probably running closer to 14.1, 14.2. If you are running on alcohol, you're closer to 9 to 1. What the O2 sensor is looking at is the oxygen content, and about 1.5% oxygen is stoichiometric, and you're breathing about 21% oxygen. So that tells you about 19 to 20% of the oxygen going into the engine is used for combustion. And it gets more complicated with the secondary air systems and aspirated converters, but a lot of that stuff is gone now. They've cleaned these engines up so much with combustion chamber technology that a lot of the emission systems aren't required, because the engines themselves aren't putting out the same COs and HCs that they used to. So an example of an open loop mode in your JK would be deceleration fuel cutoff, or clutch if you have a manual cutoff. And what that does is if you're coasting to a stop, you don't need to be pumping fuel into the engine. And the old carburetors really couldn't shut off the fuel. And a lot of them, there was something called idle transfer ports. The idle transfer ports would keep pulling that fuel into the engine, and then when you got back on the throttle, there was a real good chance that it was going to backfire. So if you had an air system, so there were anti-backfire valves or check valves, and you've probably seen diverter valves and all that, but we're not going to get into that. So when you let the gas off, you might see those O2s just drop to 0, and what that's telling you is that you are running leaner than stoichiometric, and you're in an open loop mode. Another open loop mode would be performance enrichment, or PE. When you get on the throttle, you're going up a heavy grade or a steep grade, long grade, you're towing a trailer and your engine's under a heavy load, you don't want to really be running at stoichiometric, because while stoichiometric might be the ideal compromise for power and economy and emissions and all that. It's not ideal if you're under a heavy load, and if you're under a heavy load, you could damage the engine if it leans out. So these operating systems are designed to go into an open loop performance enrichment mode. What that does is it starts putting more fuel into it. And we're going to drop down to, let's say, 13 to 1, 12 to 1. I've seen 11 to 1. The track guys like 11 to 12 to 1. They feel that builds the most horsepower up and keeps the engine safe. And that's exactly what your operating system does. One of the things you have to be careful of with the open loop mode performance enrichment is if you get a custom tune. Now, GM and all the other manufacturers basically enter the performance enrichment mode based on qualifiers: throttle position, engine vacuum, sometimes airflow, RPM, vehicle speed, and they try to basically limit it to where the engine is going to be operating in closed loop most of the time, and then only in open loop when it's required. Well, a lot of guys will get out there and they'll tweak their performance enrichment so the throttle is reduced down to 5%. Your engine vacuum, they drop it down to 50 kPa, which isn't much load at all. And before you know it, you're just going down the highway under a light load, and you're in performance enrichment, dumping fuel into the engine at 13, 12 to 1. And then you wonder why you're getting 7 miles to the gallon. And I've seen a lot of guys, especially with the Hemis. Hemis don't have air meters. They don't have mass airflow sensors. They're speed density. So that's one less piece of the pie or puzzle that feeds information to the computer. The computer can look at actual airflow in a GM system and more accurately control performance enrichment. When you're running speed density, which is basically just coolant temp, manifold vacuum, and RPM, you just don't have as many pieces of the puzzle. Now, in this LTM driving, we not only have air intake temp, which of course the Chryslers have, we have airflow, which the Chryslers don't have. We also have a humidity sensor, which the Chryslers don't have. So we're adding all this stuff together, and what the bottom line is it ends up allowing us to run in the mode that we require more often. So whether that's open loop or closed loop, performance enrichment, deceleration, fuel cutoff, there's hot protection modes, there's startup modes when the engine is cold to get it to warm up faster, and a lot of these modes are not closed loop. I've done some videos on O2s, and reading an O2, a narrow band in these vehicles is almost, it gives you most of the information that you need. I just had a customer come in, he had his rear catalytic converters removed because he's using it only off-road or mostly off-road. They ended up plugging the downstream or the bank 2 sensors into the upstreams when they did the job, and it just ran. Not only did it run terrible, but the exhaust system got loaded with fuel and turned red and was backfiring, and almost, it could have burned the vehicle down. That's how important these feedback sensors are. So you want to make sure they're right. And yes, you can remove the rear O2 sensors. Now, it is required, of course, for emissions, and most guys think it's for catalytic converter monitoring, and it is. We want to make sure we can actually check the oxygen content in the exhaust before and after the converter and see if that converter is working. Because remember, a catalytic converter's main job is to take harmful gases and turn them into harmless gases. So if you take oxygen and you start combining it with other elements like carbon, so instead of having CO, we could have CO2. Now, we know the CO2 can be a bad gas too, but it's a lot better than CO, which is partially burned fuel. We can have H2O come out of the converter, which is water. And a lot of you guys see water dripping out your tailpipe. And obviously water's a lot better than HC. HC is raw gasoline. So we can monitor the performance of the converter by having that downstream O2 sensor. Does it affect the operating system? And the answer is yes. Does it affect it a lot? I don't think so much. But there are rare cases where the computer can actually revert to the downstream oxygen sensor if it senses a fault in the upstream. Now, I've seen this mostly with Chrysler operating systems where they'll have B1S1, that's bank 1, sensor 1, that's driver's side here in the States, 4 feet from the exhaust manifold because of the turbo or whatever. Then they'll have bank 2, sensor 1, that's passenger side upstream, a foot. That's just way too far from the exhaust manifold. O2 sensors, remember, rely on heat. In the old days, we had single wire O2 sensors that didn't even work when you came to a stop. They would go into open loop because the O2 had to stay above about 700 degrees to continue to work, and when you came to an idle, it just wasn't enough heat. But you wanted to keep it as close to the manifold as you could because that's where the heat was. So you move that sensor 4 feet down the pipe, and you're going to start messing with things. Now, of course, we added heaters to the O2s a long time ago, and that allows them to stay basically closed loop all the time, even at idle, if the system wants it. But what I've seen is these superchargers, and especially the turbochargers, mess with the dynamics of the O2 system. And remember, the O2s can be programmed just like everything else. But it messes with it to the point that the computer interprets it as a failure, and it switches to downstream O2 control, which is not something you really want to do. What you want is 2 strong running upstream O2s. Do not mess around with cheap O2 sensors. Don't go to the AutoZone or whatever and get their cheapo brand for $19. You will pay the price. These modern operating systems are heavily reliant on proper oxygen sensor operation. Now, I do believe it's Nippon Denso NGK that makes a lot of the OE sensors, and you're okay to go with those, or a Delco, or of course OEGM. But I've seen, and I've actually had vehicles come in with problems where we just swap the O2 sensors out with good quality O2 sensors and it solves our problem. Remember, the heaters on these O2 sensors are monitored by the computer for performance. So if the heater resistance is wrong, you're going to have a problem. It may not be warming that O2 sensor up properly. And then, of course, the sensors are pretty much ultra fast. I've seen these ultra fast O2 sensors start switching within 10 to 15 seconds after startup, which is pretty incredible when you consider the old single wire and even dual wire. The dual wire O2 sensors are basically the sensor signal and a ground. Now, back in the day, the ground was chassis ground, which wasn't ideal because O2 sensors work in millivolts. Remember, about 450 millivolts is stoichiometric. So that's about a half a volt. And if you're running chassis ground, which is might have as much as a half a volt drop or difference between the ECM, where the ECM is sensing it, and the chassis, then that can skew things. So what happened a long time ago was most of the critical sensors went to what they call low reference. And low reference is just ground supplied by the computer. And the reason they do that is if the computer supplies the ground and it's using that same internal ground for all of its calculations, then we're going to be really accurate, even down to the millivolt, because that's what the oxygen sensors operate in. Most of the 3-wire 5-volt sensors you see, whether it's the MAP sensor or the oil pressure sensor or the fuel tank pressure sensor, that's how they operate. It's an analog signal, and I'm just getting into, I guess, a lesson here. And yes, I did used to teach emissions, so it goes kind of along with what I did. But most of the analog sensors, 3-wire, would be sensors that are somewhat important, like the MAP sensor is extremely important. So we want to have good low reference so the computer can get an accurate reading. Now, there is other ways to use sensors. One is pure analog, like a wheel speed sensor. The wheel speed sensors are basically small voltage generators, and they just put out a sine wave, up and down, up and down. And the frequency of that sine wave indicates how fast you're going. Of course, there's a table that the computer uses to look it up and says, okay, you know, when on this 52 or 53 tooth reluctor spinning around at this speed and this frequency, he's going 60 miles an hour. Really simple. It requires that dynamic movement to power the sensor, and the sensor has that strong magnet in it. But now we're not having to feed power to the sensor, which is big, because one, you're down there in the grime and the grit of the wheel, but it eliminates wires and makes the system more simple. Now, there's some other sensors that work really, really fast, and we want to get the signal as quickly as possible. And the one that I'm going to mention is going to be the MAF, or the airflow sensor. And one of the reasons a lot of the manufacturers shied away from the MAF sensor is it is a difficult sensor to keep working properly over the long term. Back in the 1980s, when GM went to the MAF tune port systems, they were awesome. I remember the old Corvettes and Camaros with a tune port. I really liked them. They were getting a lot of horsepower, great economy, and really quick throttle response. That MAF sensor was just so fast that when they dropped the MAF sensor, it was a disappointment. And they dropped it for a couple of reasons. One, it was really expensive back then to make the MAF sensor. and 2, the MAF sensor could get contaminated. It's really nothing more than a small bulb or resistor that they pump current into and try to maintain a constant temperature. And the more airflow going through it, the more that sensor cools down and the more current they got to pump in. So GM did have analog MAF sensors at first. And the problem was the MAF sensor would get contaminated, dirt, oil, you'd clean your air filter and oil would get on the MAF sensor. It was a problem. So GM did come off with what they call the MAF burn-off system. There was a MAF burn-off relay, and basically when you turn the car off, it would pump enough current into that sensor, that little bulb, to make it glow red hot, and that would effectively burn off all the contaminants, and that itself had problems because we're pulling more than 20 amps through this, all these extra wires and relays, and just got really complex. So GM finally said, screw it, and they ditched the MAF sensor, went to speed density on the next generation of the TunePort, and I must say it was a disappointment. I definitely saw a decrease in mileage, and drivability just wasn't as good in my opinion. Now, fast forward a lot of years, and let me back up a second. Back in the 90s, GM was running these MAF sensors, these analog MAF sensors in a lot of their engines, even their bread and butter V6 engines and the Luminas and the little mid-sized Pontiac Grand Ams and all that. And they did become such a problem that GM ended up doing an update where they eliminated the MAF sensor and then reprogrammed the vehicle to run off speed density. And speed density, in my opinion, is kind of a cop-out. It's kind of saying we don't want to spend the money, we don't want to spend the time, we want to lower the cost, but we're going to compromise and lose a little bit of drivability and maybe economy. Speed density is probably not going to really lose you any power. Most of the guys on the track run speed density. They don't run MAF sensors. They don't want to mess around with it, especially when you're open loop. Who cares? You're just dumping fuel into the engine. But for a vehicle that's going to be driven on the road for hundreds of thousands of miles, I think in the long run, it's an advantage. And I think that is one advantage that the GM engines have in general over the Chrysler engines. So what GM did is they went to a digital signal to the MAF sensor. And there's even a step above that, and we're going to talk about that in a second. But digital means that GM is now putting a frequency out, and it's extremely fast. So we have now power and ground. We don't need low reference anymore. Low reference is when the computer requires a feedback signal dependent on resistance. So that may be true with an oxygen sensor, and it may be true with the 3-wire analog sensors, but it's not really true with a digital signal. And the reason is frequency is frequency. You can increase the voltage, decrease the voltage. You can have a voltage drop across the power side. You can have a voltage drop across the ground side. It's really not going to affect that frequency. So it's kind of a backup to the MAF sensor to make it one step more robust by having power and ground, doesn't matter where it comes from, and then have this signal a frequency. And it's super fast. If you look at a MAF sensor signal, that airflow is changing many times a second. That is what gives you that extra throttle response and drivability, in my opinion. Now, of course, if the sensor does get contaminated, you over oil your air filter, you're out in the trail, and you're at the back of a wagon train, and you just suck in a lot of dirt, of course, that's going to affect the performance of the MAF. And the MAF systems have a built-in limp mode. Let's just say your air filter fell off, or you had an intake leak, or the sensor got too contaminated. The system will recognize that, and then it'll go into a limp mode. And most of the limp modes are just basically speed density. They now take away the airflow calculation and kick it into a speed density only, so you're running off the map. And it works. And while we're on this subject, let's talk a little bit more about the technology of these LTs, because it is pretty impressive. In 14, 15, 16, GM used a 4-wire high-pressure fuel rail sensor. And it was 4 wires with 2 signals. Well, in about 17, they went to a 3-wire sensor, got 4 signals out of it. You say, well, how do they do that? Well, I'm not exactly sure, but it is some kind of a serial communication network between the computer and that sensor. So we now went from 4 wires to 3, and we've doubled the amount of feedback from that sensor. So we've simplified things, and the 3-wire sensor, while some guys say, oh, it's not as good as a 4, it's actually better. And they did the same thing now with the newer MAF sensors. We were getting up to 9 wires, I think, with the LT MAF sensor, because we have an intake air temp sensor. We, of course, have our airflow MAF sensor. We had our humidity sensor. We had a lot of wires going into this thing. So I do believe on the LED7 and the LED4, GM has serialized that sensor, reduced the wire count. I think it's 4 or 5 wires now, and don't quote me on that. But I'm going to look into it. But I think there's a serial network between the ECM and the modern MAF sensor and the LT. And again, we're getting more pieces to that puzzle. We're getting more information so that we can more accurately control the fuel and spark delivery. Now, I know I'm getting a little bit too far into this, and if you guys like this kind of talk, let me know in the comments, and you know, I'll go into more detail. For right now, just know that if you get some custom tuning done, and like I'm cruising right now 70 to 80 miles an hour out here in northern Utah, we got a lot of grades. I'm going up a grade right now, and then I'm going to go down to downhill, and then I'm going to go up another grade, and it's just going to be up and down right up through Cedar City, where it just gets higher and higher and higher. Well, in a lot of these grades, if you have a pimped out operating system, you could be in open loop and just dumping fuel into the engine unnecessarily. In a lot of cases with a stock operating system, if you have larger tires and you're towing a trailer or whatever, just backing off a few percent on the throttle can kick you back into open loop and significantly improve your economy. I did a video on that a couple of years ago, and I've had, I don't even know, but many customers call me and say, you know what, Robbie, I started looking at my gauge, whether I was an open or closed loop, and it made a huge difference. I picked up 3 miles to the gallon just looking at what I was doing, and I wasn't even going that much slower. It was just a couple of miles an hour slower, and I picked up that much economy. All right, I've yacked enough. I'm going to try to do a little more yakking when we get down to the trail. We've stopped to do a drone battery change. Let's take a look at this LT1 under the hood. We got our Motec battery tray here. You can see how much room that gives us between the engine and the battery and the TIPM. Keeps the heat away from those electronics. We got a K&N filter. This is an RF-1033 if you guys are interested. We've got our coolant overflow bottle here. We got our quad header radiator. We have not installed the upper valance yet. We got some new ones being powder coated. This is a full-on LT1 2019-2020 Corvette. You can hear this fan. I don't know if you can see it, but I got the air conditioning on inside. It's kind of a warm day, and it's keeping the drone cool. So you're hearing that fan wind up. It's not winding up a whole lot, but you can see that we got cold air blowing here on the drone. If that SS fan was at full speed, I could barely talk. So it's probably running about 15–20% to keep this engine cool and keep the air conditioning going. Now, speaking of cooling, this isn't too bad. We've got a hoop, a winch, which is semi-sunk, and a control box on top of it. One good thing is we do have all the grill openings unobstructed as far as screens and mesh or whatever else guys put in there. But I think you can see in this position we do have some blockage, especially at speed. We're going to have a high pressure bubble here that's going to force the air over the hood. So what I would do in this situation, this winch is pretty good, being semi-sunk, but I would take this control box off and move it to the side. That's what I did in my Jeep. If you guys really need these stingers, go for it. Personally, if you don't need it, I would take it off. I don't see any marks on this thing. I doubt it's ever been used. So that's just going to open up some more air, because at high speed, when the air hits this, even as small as this is, it will deflect that air away from the grill. So you got high pressure inside this engine compartment. You got low pressure out here. We got to suck it in with a fan. So why make it suck through a straw? If you don't need obstructions in front of your grill, get rid of them. Not sure if you can hear this, but this LT1 is pretty much as mild as can be. We're about 500 RPM right now. Notice there's absolutely no lump. We're gonna get back on the trail.